Hi, welcome back students. This quarter, we are studying CSS or Computer System Servicing, which is now known as Computer Software Servicing. Just like in our previous video lessons, if you have limited data or internet connectivity, you may just read the written explanation that this video will contain. I will post that in our group chat or GC. But if you can find ways to watch this video, that will be of much help to you, especially that this lesson is one of the hardest. Last week, we have learned about memory. Again, in CSS, memory refers to a physical device that is used to store information temporarily or permanently for immediate use in a computer. We have two memories in our computers. We have the read-only memory or ROM, which is a type of memory that is responsible for the booting up the computer system, including loading the operating system, and random access memory or RAM, which temporarily stores data for programs that are being accessed by the CPU. I know that you have been wondering why are you seeing numbers in your module for this week. Some of you may be confused, but yes, our lesson for this week involves computation. That is also the reason why I chose to make a video about this topic. TLE 4th quarter week 6, carry out measurement and calculation. Let us first set our goals for this week. So we have three goals. First is to perform calculation needed to complete tasks using the four mathematical fundamental operations: addition, subtraction, multiplication, and division. Second is use calculation involving fractions, percentage, and mixed numbers to complete workplace tasks. And last, the self-check and correct numerical computation for accuracy. Let us define mensuration. So mensuration is a geometry applied to the computation of lengths, areas, or volumes from given dimensions or angles. Or simply, it is the act of measuring in CSS. We will not be using measuring tools. It instead uses virtual measurements. We will only be using numbers 0 and 1. They are called binary digits. So bit refers to an abbreviation of binary digit. It is also represents the smallest piece of data. Computers can only interpret patterns of bits. So binary number can also be called machine code. Always take note that the binary has a base or radix of 2. Here is the American Standard Code for Information Interchange or ASCII. It is a commonly used code where each character is represented by a string of bits. For example, if we refer to the table, capital letter B, when we say capital letter B or when we say capital letter, it is the uppercase of the letter. So capital letter B is equal to 0, 1, 0, 0, 0, 0, 1, 0. So it is equal to number 66. Small letter b. Again, when we say small letter b, it is the lower case of the letter. So small letter b is equal to 0, 1, 1, 0, 0, 0, 1, 0, or it is equal to number 98. Okay, for our attendance for this week, identify the binary and ASCII code or number of the letter capital X. Comment your answers in our group chat. Please refer to the table in your module. Okay, so how do we convert decimal numbers to binary? In mathematics, decimal is a shorthand way to write fractions and mixed numbers with denominators that are powers of 10, like 10, hundreds, thousands, 10,000s, etc. While in computer, decimal number system is a base 10 number system having 10 digits from 0 to 9. This means that any numerical quantity can be represented using these 10 digits. Decimal number system is also a positional value system. This means that the value of digits will depend on its position. If the radix or base of binary is 2, the base of decimal is 10. Again, it has 10 symbols, 0 to 9. Example, 8, 10. Looking at the table, 80 is 0, 1, 0, 1, 0, 0, 0. So how do we compute that? Then let's just follow the steps. Step 1. To convert a decimal number to binary, you need to do is divide the number by 2. Our first example is number 80. So 80 divided by 2 is 40. Then next step, step number 2, get the quotient and the remainder. So 80 divided by 2 is equal to 40. Then the quotient is 40 and the remainder is 0. So next step, step number 3, bring down the quotient, divide it by 2, and get the quotient and remainder again. So 40 divided by 2 is 20, remainder is 0. Then 20 divided by 2 is equal to 10, the remainder again is 0. Then 10 divided by 2, uh, the answer is 5. The remainder again is 0. Then 5 divided by 2, the answer is 2, but there's a remainder. The remainder is 1. Then 2 divided by 2 is equal to 1. The remainder is 0. So step number 4. Do it repeatedly until the quotient results to 0. So 1 divided by 2 is equal to 0, but the remainder is 1. Then step number 5, last step, copy the remainder from bottom to top. Again, copy the remainder from bottom to top, and that is the binary equivalent. So based on your answers or our answers, the binary number is, or the binary equivalent is, so 80, 10 is equivalent to 0, 1, 0, 1, 0, 0, 0, 0. To check, let's convert from binary to decimal. So to convert easily, let us make a table. On the first row, write the binary equivalent. So 0, 1, 0, 1, 0, 0, 0, 0. So on the second row, from left to right, you will have to double the value starting with 1. So 1 plus 1 or times 1 is equal to 1. Then 2 plus 2 is equal to 4. And then so on. 4 plus 4 is equal to 8. Then 8 plus 8 is equal to 16, and so on and so forth. You just have to add the values where there is 1 and just disregard those values where lies or where 0 lies. So 64 plus 16 is equal to or equals to 80. Again, let's try. Convert the decimal number to binary. Compute for the binary of the decimal 97. Try to solve. I will give you a minute to answer. Timer starts now. Okay, 5, 4, 3, 2, 1, 0. Okay. So, looking at the table, did you get the same answer? So, 97 divided by 2 is equal to 48. The remainder is 1. And so on and so forth, and so on and so forth. Okay? So 97 is equivalent to 11000001. So let's check by trying to convert binary to decimal. Okay, convert binary to decimal. First row is 11000001. Then the second row is, okay, again, I will give you a minute again to answer. Timer starts now. 56, 55. 5, 4, 3, 2, 1. And so, starting from right to left, again, 1 plus 1 is equal to 2. Then 2 plus 2 is equals to 4. 4 plus 4 is equals to 8. And so on and so forth. So, did you get the same answer? 64 plus 32 plus 1 is equals to 97 because they hit the 1. So, great. Now, if you still have questions regarding the computation, just send me a message and I will call you to explain further. Got it? Okay, very good. Now, we will proceed with calculating data storage. So, byte is the most basic unit of digital storage. 1 byte is equivalent to 8 bits, which is the smallest unit of measurement or measure or UOM used to represent the data storage capacity. The terminology such as bytes or B, kilobytes, KB, megabytes, MB, gigabytes, GB, and terabytes, TB, are used to refer a storage space. Did you know that the smallest representation of data is called bit? Then byte is the most basic unit of digital storage, which is equivalent to 8 bits. Letters capital A to Z is equal to 1 byte. Then bit is equals to 0 and 1. So here's the byte conversion table. So 1 kilobytes or 1 KB is equal to 1024 bytes. Then 1 megabytes is equals to 1,048,576 bytes. Next is 1 gigabyte. 1 gigabyte is equals to 1,73,741,824 bytes. Then 1 terabyte is equals to 1,099,511,627,776 bytes. Woo! So, Here's the components. Let's say you have compact disc or CD. Its capacity is 700 MB or 700 megabytes. Then next is digital versatile disc or DVD. If single layered, it has 4.3 gigabyte. If dual layered, it has 8.5 gigabytes. In Blu-ray disc, if single layered, it has 25 gigabytes. If dual layered, it has 50 gigabytes capacity. Once we know the total file, once we know the total file size of a folder, it is now easy to determine the total. The total number of bytes or file that can be placed in our device. For example, how many 15 kilobytes or 15 KB JPEG or JPG files can be stored on a 1 megabytes folder in your hard drive? JPG files or JPEG files refers to the ones saved as a picture. So here's the solution. A file is 15 KB in size, right? Then 1 KB referring to the table is 1024 bytes. 15 multiplied to 1024 is equals to 15,360 bytes. So it is equal to 15 KB file or 15 kilobytes file. Then 1 megabytes or 1 MB is equals to 1,048,576. Then 1,048,576 MB divided by 15,360 bytes is equals to 68.266 or 68 kilobytes files or KB files can be stored in 1 MB folder. Let's try again. How many 5 MB files can be stored in a 1 gigabyte flash drive? Again, I will give you a minute to answer. Timer starts now. Okay, 5, 4, 3, 2, 1. Timer stop. Okay, from the given, our file size is equals to 5 MB. The storage is 1 GB. So simply multiply 5 MB to 1,048,576 bytes, and it equals to 5,242,880 bytes. Then 1 gigabyte is equals to 1,073,741,824 bytes. Then 1,073,741,824 bytes divided by 1,048,576 is equals to 1,024 of files with 5 MB can be stored in 1 GB flash drive. Did you get it? Did you get the same answer? If yes, then that's great. Then if not, please send me a message to clarify your thoughts. Okay, to end our lesson for this week, may I just leave you a quotation from Bill Gates. He said that computers have lots of memory but no imagination. It means that computer can store many information but cannot create by himself. It only depends on what is given to him. We are the content creators. Everything that we input our computer is what it stores. Make sure to keep storing relevant files, information, and make use of it to store happy memories. Happy weekend!